let me tell you about a sort of another type of induction in some sense. So the type of induction we've been talking about is something called weak induction. So the idea was that if P1 is true, basically, well, I mean, it's kind of like an argument. It's like P1 and Pn implies Pn plus 1, therefore, for all n, Pn or something. Or in other words, yeah, maybe I don't want to write it like this. You know, if P1 is true and Pn logically implies Pn plus 1, then Pn is true for all n at least 1. Okay, I mean, this was how we wrote it before. Now here's the thing. Suppose I know P1 is true and P1 implies P2. Then by modus ponens or whatever, you know P2 is true. But now at that point, okay, in weak induction we would just say we're going to use P2 to get P3, and we're going to use P3 to get P4, and so on. But if you think about it, if I know that P1 and P2 are true, I could use both of them to get P3, because I know they're both true. And then once you know P1, P2, and P3 are true, if you wanted to, you could use all of them to get P4. And if you know P1, 2, 3, and 4 are true, you could use all 4 of them to get P5. And that would also prove it for all n. So that's something called strong induction. So if P1 is true, and when I take P1, the statement P1 and P2, and dot, 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 up to Pn, so if this logically implies Pn plus 1 for n at least 1, then Pn is true for all natural numbers n, or all n at least 1, or whatever. Okay. It's again kind of like dominoes, except it's kind of weird dominoes where to knock over the n plus 1th domino, you need to use all the dominoes that came before it. But is it clear why this should be true, or why this works? I mean, it works by very much the same principle as the weak induction, except it uses the fact that you could use, if you wanted to, you can use you can use all the previous statements if you want to drive the next statement. I want to give you an example which uses strong induction. Integer at least 8 can be written as a sum of 3s and 5s. When I say a sum of 3s and 5s, I mean like with positive coefficients. So like in really kind of technical terms, what I'm saying here is for all n at least 8, there exists, let's say, x at least 0, there exists y at least 0. Writing in this really technical way helps you or not, but this is what I mean. So I want to prove this by induction on n. So what should I do for my basis? Yeah, so at least the case n equals 8, right? Because that's basis here. It's going to turn out, we're going to see in the proof that it's useful to actually prove it for more than just the first base case, but certainly we want to start with the base case, so the first case. So, you know, consider the case n equals 8. Exactly, yeah. So, okay, 8 is 3 plus 5, so it is a sum of 3s and 5s. Now, here's the thing to think about. Suppose I know it's true for 8. Does that help me prove it for 9? And it sort of doesn't, right? If I know it's true for 8, that means I can write 8 as 3s and 5s, but I can't just use that to get 9 in some sense. So it's not particularly useful to know the case 8 to get the case 9. So I'm not really going to be able to do induction. So it's going to be useful to prove a few more base cases, or basis cases, n equals 9. And again, this one's, I mean, usually in these things, the basis cases are pretty easy, right? So that's 9 is 3 plus 3 plus 3. If you think about it, if I already know 8 and 9, it also doesn't really help me get 10. it's going to give me 11 or 13. And so we're good. For n between 8 and 10. Like this before, right? Where I've proved, several basis cases. I think the reason for proving, several basis cases is sort of what I'm trying to explain there with trying to think of whether it helps you, right? So, in some sense, knowing the answer for 8 doesn't really help. Knowing 9 doesn't help you get. But suppose I know that these 3 cases are true. How do I get 11? Okay, that's true. But I sort of want to do this inductively based on the. Was there another hand? Yep. Exactly. So since I'm trying to do 11, I know that 8 works. I can always just add 3 to whatever solution I got for 8. I can just add 3 to it, right? Now I'm trying to do 12, and I know that 8, 9, 10, and 11 all work. So, okay, I can ignore most of those, and I can just look at 9. Oh, I've got a solution for 9. I can add 3 to it, right? So that's how the induction works here. So here's how my induction is going to work. And I'm going to use strong induction. So to prove the case for some number n plus 1, and I'm going to assume all the cases up to n. So let n be at least 10, because I've already proven it up to 10, so I can assume it works for 8. I can assume it works up to 10. So and assume that every between 8 and 10, so such that k is between 8 and n, written as a sum 3's. So this is so remember, induction hypothesis is always an assumption, right? I'm assuming that the early cases, can be proved, and I want to prove the next case. So we want to show that of 3's and 5's. Okay. So based on the kind of idea we were talking about here, does anyone have any kind of idea how I'll do this? So if you think about it, imagine we're proving the case 11, right? N equals 11, or in this case, n plus 1 is 11, right? To prove 11, we use that 8 is true, and we add 3 to it. And we add 3 to it. So to prove n plus 1, what I want to do is use the fact that it's true for the value which is 3 lower than this, which is n minus 2, right? And then I want to just add 3 to it. Is kind of clear? So, okay. One thing is, so how do I know that? So I want to use that it's true for that n minus 2 can be written lives. How do I know that that's actually true? Is a bit of an issue. So So 8, or at least 8. In our assumption, we have n at least 10, so n minus 2 is at least 8. So since n is at least 10, we know that n. So we can apply the inductive hypothesis to n minus 2 to get it as a 5s. So in other words, I mean, if I want to really kind of solidify this, do this kind of algebra, words, n minus 2 for some x and y. Okay. Therefore, if I just add 3 sides, equal to 3x plus 1 plus 5 y. So therefore, plus 1 is of 3's. Okay. Is this weird? A little bit weird, right? Because usually in these induction things, we use the case for n to derive n plus 1. But here we're using n minus 2, which is a little weird, but yeah. So conclusion is a sum of 3's and 5's. Okay. Any questions about that? Yeah. Sorry, when I was putting the base cases. Yeah. Yeah, that is a good observation. So yeah, so as was said, so we did 3. The number 3 was the smallest. Yeah, it does make sense to do 3 base cases in that case. Because, so actually, I mean, more generally, like why you would do a certain number of base cases is based on how many steps you have to. So if I want to do a certain step, I need to look backwards in order to do that. Here, to get 8 and then do 11. So that kind of tells you how many base cases to do in some sense. Yeah, but that's a very good question. Any other questions? Okay. We still got, so let's do another one, another example. Another example where we need more than one base case. Let O be 1, A1 be equal to 2. So it's another one that we've done one of these before, right? One of these things with, I hope we haven't done this. Maybe somebody can shout at me if they remember seeing this already. So A0 times AN minus 1 plus 3, or 2 minus 2 times AN minus 2. And we want to prove AN 2 to the n for all n at least 1. Or sorry, n at least 0. Okay. Now, I'm not sure whether these recursive definitions, if it's clear to everybody. I think let's write down a few values. You don't have to do this if you're proving something, but it doesn't hurt. So if n is, know that an is 1, because a0 is 1. If n is 1, an is 2. If n is 2, by definition, so this thing says that a2, well, so 3 times 2 times a1, 2, so it's like 12 minus 4, which is 8, right? And so you can see a sort of pattern. This does look like the powers of 2 for all n. Okay. So is it clear how I'm kind of computing these things? Okay. Okay. So let's look here. So I'm going to prove this by induction. But here's the thing. So this is kind of relating to the previous comment. So if I want to know that something is true for an, just by this formula, you kind of need to look at two previous, n equals 0. So the left-hand side, 1, so that's good. For n equals 1, left-hand side is a1, which is 2. Right-hand side is 2 to the 1, which is 2. And so that one's good, too. In terms of communicating, kind of a way to explain the proof in the basis cases, don't just write 1 equals 1, because I know 1 equals, what does that tell me? The point is the left-hand side equals the right-hand side. Hypothesis. So I'm going to go through this one a bit quick, because we do need to set up for the test pretty. So I let n be at least 1, and assume that, so we're going to use strong induction. I'm going to assume that ak is equal to 2 to the k for all k between 0 and n. So we assume, okay. So, okay, what do we want to prove for the inductive step? Rather than necessarily proving it. Oh, yeah. Yeah, you want to prove the n plus 1 case. So we want to show, so the n plus 1 case 2 to the n plus 1. Okay. Well, the left-hand side. So the left-hand side is an plus 1. So, okay, what did our formula for an say? It says that an is equal to 3 minus 2an for n at least 2. Okay. This might look a little weird because this is an n and that's an n plus 1. But, I mean, basically any case is equal to 3 times the previous case minus 2 times the case before that is the key idea here. So this should be 3an minus 2 an minus 1. You could kind of think of substituting, but this only works because n plus 1 is at least 2. Right? Because we assume, so therefore this formula holds. And now what do I do? So we've written plus 1 case in terms of these earlier cases. Well, by the inductive hypothesis, I know what these earlier cases are, right? I know that, for example, the k for all k between 0 and n. So in particular, if you plug in, know that an is 2 to the n. You can just write that down. And I know an minus 1 is 2 to the n minus 1. So this is 3 times 2 to the n minus 2 times 2 to the n minus 1, which is 3 times 2 to the n minus 2 to the n, 2 times 2 to the n, which is 2 to the n. But the conclusion is an equals 2 for all n, at least 0. So this here is just a bit of algebra, but yeah.